Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 20, 2025, which was about 4 days ago. The standout result is an adaptive scheduling method that stays near hindsight optimal while using only lower bound predictions, with a competitive ratio that grows only logarithmically in alpha inverse, so it remains robust even when predictions are very uncertain. The paper is titled, Adaptively Robust LLM Inference Optimization Under Prediction Uncertainty. And as we will see later, the practical impact on serving efficiency is compelling. In short, the work compares conservative and adaptive batching under memory limits and shows consistent gains on real chat traces. Building on that, the featured tweet claims current schedulers are overly pessimistic, making systems about 5 times slower, and praises the adaptive method for performing nearly like a perfect all-knowing scheduler. Engagement looks solid with about 137 likes. Alright. We are looking at a plot that charts the competitive ratio against the upper bound U, which captures how uncertain the outputs can be. You can see the red data points hugging a smooth blue logarithmic fit, so performance grows slowly with U rather than exploding. The curve starts near 1.4 and rises toward a bit above 3 as U approaches 2000, which matches the logarithmic guarantee. The inset legend confirms an excellent fit, indicating that the adaptive method remains stable across wide uncertainty. Now we are looking at a figure that plots competitive ratio on the vertical axis against alpha, the lower to upper length ratio, on the horizontal axis. You can see the gold curve for the conservative method rising sharply as alpha grows toward 1, which signals worsening performance when intervals are tight. The red line for the adaptive method slopes downward, so it improves as predictions tighten. A dashed vertical line, near 0.38, marks the crossover, where the adaptive method starts to dominate. Next, we are looking at 2 side-by-side plots showing how the competitive ratio changes with the parameter Q. The left panel climbs from about 1 to roughly 1.7 as Q approaches 1, which signals steady but diminishing increases. The right panel shows a similar rise that levels off sooner, topping near 1.5. Together, these curves illustrate that the adaptive strategy remains bounded and improves smoothly as the distribution becomes heavier toward shorter outputs. Now we are looking at a 2-panel histogram that summarizes input and output word counts from the chat traces. The left panel shows inputs are very short for most requests, with a median near 11 and a long right tail, which means occasional long prompts exist. The right panel shows outputs are longer on average, with a median around 43 and a heavier tail, so responses often dominate memory. Together, these distributions explain why adaptive scheduling must handle skewed lengths without overcommitting memory. Now we are looking at a line plot comparing average latency versus the number of requests under a very coarse interval from 1 to 1000. You can see the green benchmark stays lowest and grows gently, while the blue adaptive line tracks it closely, which shows near hindsight performance as load increases. The orange conservative line climbs steeply, so latency balloons with more requests. This widening gap highlights how cautious overestimation wastes memory headroom and stretches queues. Here we are looking at a line chart that compares average latency against the number of requests under coarse interval predictions. The green benchmark stays lowest and grows steadily, while the blue adaptive line almost overlaps it, which signals near hindsight performance as load rises. The orange conservative curve climbs much faster, so queues lengthen and latency inflates. The legend at the top left clarifies the mapping between colors and methods, and the axes label the scale of latency and request volume. We are looking at a single line chart of average latency versus the number of requests, with a legend showing 3 methods at multiple confidence levels. You can see the green benchmark staying lowest as load rises, which serves as a hindsight reference. The blue adaptive curves closely trail the green line across all request counts, so performance remains near optimal, even with coarse and tight intervals. Meanwhile, the orange conservative curves climb much faster, especially at low confidence levels, because overestimation wastes memory and lengthens queues. Building on that, 2 takeaways stand out. First, adaptive underestimation with dynamic refinement beats conservative overestimation, yielding near hindsight latency even with very coarse intervals. Second, robustness grows with tighter predictions while remaining bounded when confidence is low. A prediction interval means a lower and upper guess for output length. I am Alex. Thanks for listening to AI Research Roundup.